All right, so there's a direct correlation between Ka and Kb. We can completely relate these two entities by that equation right there. You should remember this from lecture last week where we talked about Kw is equal to the hydrogen ion concentration times the hydroxide ion concentration, don't know what just happened there, which is equal to 1.0 times 10 to the minus 14. Again, don't know what's going on with my little lines there. Sorry about that. So Ka and Kb can be directly correlated with the autoionization of water. So we can also say that this is, we can also say that this is equal to 1.0 times 10 to the minus 14 because Kw, the autoionization of water, is equal to 1.0 times 10 to the minus 14. So this is a really important equation you need to know. You need to know it like you know how to add 2 plus 2. So if we know one of them, we can calculate the other. All we need to do is know one of the two because we know that Kw equals this. That will always be true. So reactions of anions with water means that anions are the bases, meaning they can accept a hydrogen, and cations, or the positive sign entities that form, will behave as acids because they can then donate in the reverse reaction the hydrogen they originally picked up. So if we look at this hydrolysis reaction where we form hydroxides and the conjugate acid, this is what we know to be true. So we can see there's clearly an anion here, and the anion is a base because it can accept a hydrogen ion. We know it can accept a hydrogen ion because it has that negative charge. It wants to get back to neutral. So if we're looking at this and we see that negative charge, you should immediately be thinking, that's got a negative sign, too many electrons, so it can accept a hydrogen from something else in solution. Therefore, this is going to be the base. If we look at the products, we can see that X absolutely did accept a hydrogen, and this is the conjugate acid. Likewise, if we look at water, which we don't include in the actual formula for Ka or Kb's, what we see is that it starts off with 2 hydrogens and winds up with only 1. That means somewhere along the line, it donated a hydrogen. If it donates a hydrogen, it is behaving as an acid, and the hydroxide anion in the reverse reaction will behave as a conjugate base. Because in the reverse reaction, this now can pick up a hydrogen going back and becoming this. Remember, these reversible reactions are occurring simultaneously. The forward and the reverse reaction are occurring simultaneously until we reach equilibrium. And equilibrium means the rate of the forward equals the rate of the reverse reaction. This does not mean the concentrations of any species present are equal. It just means that the rates are equal. So what's really kind of going on here? If you look at this picture, what you can see is that this FeHO26 plus 3 becomes a plus 2. we go from +3 to +2. That means at some point, something has happened. Has it gained or lost an electron? Well, because +3 means 3 electrons, I don't know how many, 3 electrons lost, and +2 means 2 electrons lost. That must mean that somewhere between the reactant and the product, that forward reaction, something is gained, a hydrogen is gained. And you can see here that oxygen that did not have another hydrogen has been picked up. Okay? All right. So what this also means is that this water has gained a hydrogen. It's gone from H2O to H3O plus. So man, all right, now what's going on? If you could take this, let me change colors. No, don't want that one, I want green. If you could take this entity right here and write it as FeH2O, I'm sorry, I'm writing like a kindergartner, 5, that means what we have on the outside is OH. Remember, because there were 6, now there's 5, so I'm just pulling off an OH, putting it to the side. It is this hydrogen that goes here. Okay, yes, I realize there's a little typo there. I hope you caught that. The point is, the big picture is that right here, cations with acidic protons like NH4+ will lower the pH of the solution. That should make sense to you because this NH4+ will eventually revert to NH3 and lose a proton into solution. So if I have more hydrogen ions in solution, that means a lower numerical number of pH. A lower numerical number of pH means more acidic. Okay? So, when we're talking about cations with water, the larger the charge and smaller the size, the more acidic. This is a takeaway that you need to have. Larger the charge, greater the charge, smaller the size, more acidic. Generally, what we do is we look to size first and then charge. So if we have two things that are similar in size, we're going to immediately revert to looking at what the charges are. If we have something that's similar in charge, we're going to look to the size. So whatever we got going on, specifically with metal cations, we're going to say, okay, what's going on? All right. If you look at, for example, Fe2+ and zinc 2+, they have a similar charge. So which one, I'm sorry, I said charge. Yeah, they have the same charge. So which one has the smaller size? If you look on your periodic table, I'm just flipping to mine right now, you will see that iron is to the left on the periodic table of zinc, which is further to the right. If you remember your periodic trends, as we go from left to right on the periodic table, we do have an decreasing size. All right. So there's a couple of things that are at play here. your best bet is just to focus on the numbers. These are very similar Kas because the reality is their size and charge are very, very similar. But if I were to compare just, what happened here? If I were to compare just iron 2+ with aluminum 3+, you will see that this Ka is much closer to 1, so it's much more acidic for a couple of reasons. The higher charge makes it a smaller size. The higher the charge means more electrons are going away. So the more electrons that are going away, the smaller the size. So it's easier to compare very different things than things that are relatively close. All right, and for my purposes and your testing purposes, I'm going to focus on the things that are different. So when we talk about the effect of cations and anions, we know that the anion is the conjugate base of a strong acid. And that conjugate base of a strong acid does not affect the pH. By the way, numbers 1, 2, and 3, you need to memorize like you know how to add 2 + 2. Okay. The anion that is a conjugate base of a weak acid increases the pH. Why? Because if it's a conjugate base of a weak acid, that means the conjugate base is very small. I just totally said that backwards because I'm getting ahead of myself. I am very sorry. Weak acids have a strong conjugate base, meaning their Kb is very small. I'm sorry about that. I apologize. Weak acids have a strong conjugate base. Strong acids have a weak conjugate base. If we have a strong conjugate base, that means the reverse reaction will be spitting off hydrogens that it originally accepted to become a base. A cation that is the conjugate acid of a weak base will decrease the pH. And when we say increase and decrease, we're talking about numerically. So if I have a weak base, its conjugate acid is very strong. That conjugate acid means it'll spit off hydrogens, putting more into solution. Weak acids, strong base. Base are the acceptors. Acids are the donators. If the conjugate is a strong base, it will accept lots of the hydrogens and increase the pH to become more basic. If the acids, conjugate acids, are very strong, it'll donate in the reverse reaction many hydrogens to numerically decrease the pH to make it more acidic. So cations of strong Arrhenius, we're not going to worry about. I'm not going to worry about Arrhenius for you guys. We're only going to focus on the Bronsted-Lowry. And other factors that affect acid strength, you have to look at things like polarity. All right. The more polar the hydrogen anion, or in most cases, halogen bond, or the weaker the bond, the more acidic. So the more polar and weaker the bond, the more acidic. Remember, we said strong acids are a direct relationship, not to strong intermolecular forces or intramolecular forces, but because they're weaker, that means they very easily disassociate into solution. So if they very easily disassociate into solution, they're going to be more acidic. General rule of thumb, the level of how acidic something is increases from left to right and top to bottom. So over to the right and down the periodic table increases acidity. That is because the intramolecular forces are weaker, so more of them can break apart and ionize in solution. So when we talk about oxyacids, remember these are the acids that have polyatomics. For example, H2SO4, HNO3, H2CO3, etc. These oxyacids, where a hydroxide is bonded to another atom Y, the more electronegative Y is, the more acidic the acid. This is a poorly written slide because we're really talking about the conjugate acid here. Okay. I'm not going to worry about this with you, except as a good rule of thumb or a trick, is that the number of oxygens increases acidity. So the more oxygens that are present, the more acidic the compound is.